How do you know whether it is a laser or LED? Both are emitting light. You can control the spectrum, the spectral width of both. You know, laser is monochromatic, so you can potentially say that I can look at the spectrum, and if it is narrow, it is a laser, if it's broad, it's an LED. But I could always put a filter at the output of LED and get narrow light out of LED. So that's also not a conclusive way of saying that the source is emitting, doing spontaneous emission or stimulate. The conclusive way is this: Li characteristics. You increase the current through the device. You measure the optical power. If it's a straight line passing through origin, then it is a device that is undergoing spontaneous emission. If you see a threshold characteristics that I said we will do later, why a laser should have threshold, it is a stimulated emission mechanism. Now we want to talk about quantum efficiency. So we talked about internal quantum efficiency, which is a measure of the fraction of recombinations that is leading to photon emission. We said of all the recombinations, all of them need not result in photon emission. They may result in Auger recombinations or other recombinations, defect states where you get phonons, you do not get light out. So we already talked about internal quantum efficiency. Now once the photons are released from the recombination, what really happens? Do you get all of them out of the system? And the answer is no. And what are the mechanisms by which you have losses inside? That is given by your external, that is quantified through your external quantum efficiency. The first one is loss due to total internal reflection. So let us say the emission is happening, I mean I have just marked it as a surface emitting structure right now, right. So assume that this P region or this N region is transparent and light can come out of this structure. I know that, let us say the photon is, or I am using photon and light ray interchangeably here, okay. So the direction of movement of photon is marked as the direction of ray of light here, okay. So let us say the direction of emission is this, okay. You have a refractive index N here, this is N type and this is P type, but you have a certain refractive index of the material here, and for convenience let us say that it is emitting only from this side, right. You have created a hole or you have created a window where the emission is happening only from one side, it could be P side, N side, does not matter. Now the light ray is reaching here. What happens to that at this interface? You have refractive index N here, you have refractive index 1 here. So you have an impedance mismatch. Refractive index is proportional to the impedance. So whenever you have an electromagnetic wave, so we will keep using wave, photon and ray interchangeably, okay. So whenever you have an electromagnetic wave incidenting an interface where the constitutive parameters are different, your epsilon mu is different, what happens? You could have reflection, only a fraction of it will get transmitted, and that loss is given by your Fresnel coefficients, okay. So this you would have done in your basic electromagnetics, right. So because of the change in the constitutive parameters, the wave experience, so you have a certain fraction, that is, you have a certain fraction of light that is transmitted and a certain fraction that is reflected, and the reflection coefficient if you have a medium whose refractive index is N1 and another medium refractive index N2, and you have a wave hitting from N1 to N2, the reflection coefficient is given by N1 minus N2 by N1 plus N2, and in our case N1 is N minus 1 divided by N plus 1, and the reflectance, which is the ratio of powers, and ratio of power would be proportional to the square of the ratio of the field, and so this must be equal to n minus 1 by n plus 1 the whole square. As far as capital R is concerned, it may not matter whether you write it as n minus 1 or 1 minus n, but here for ratio of fields it will matter, because depending on the, if you have put a wrong sign, the phase change will be different. And this is your Fresnel reflection. So, but then we are not interested in finding out how much is reflected, we are interested in finding out how much is transmitted, how much is available outside the system, and so that must be equal to, so fraction of power available at the output because of Fresnel reflection, we are talking about only Fresnel reflection, is 1 minus n minus 1 the whole square by n plus 1 the whole square. And if you expand this, it is n plus 1 the whole square minus n minus 1 the whole square divided by n plus 1 the whole square. So, your answer would look like 4n divided by n plus 1 the whole square. We can call this as efficiency eta 1. It means that of the entire power that got emitted inside the material, only a fraction eta 1 of it is available outside because of the fact that there is Fresnel reflection, there is a change in medium. The question to ask is this large, is this small? Ideally you want this to be 1 or 100%, but it is definitely not 1 because it is 4n by n plus 1 the whole square. So, the question is, what is it for practical devices? So, let us say a typical semiconductor material. What is a typical semiconductor material now? Gallium nitride or indium gallium arsenide phosphide, right. So, N for that material is approximately, let us say 3.5. It could be 3.6, it could be 3.4 depending on the band gap, actual band gap of the material. But roughly the order of magnitude is 3.5. It is not like glass which is 1.5, it is a high index material. So, can you calculate what is eta 1 because of Fresnel reflection? So, this is nothing but 4 into 3.5 divided by 3.5 plus 1 the whole square, 0.691, which I can write in percentage as 69.1%. And what happens as your refractive index increases? Band gap increases. When band gap increases, your wavelength of emission will increase or decrease. Band gap increases, the wavelength of emission frequency increases, wavelength decreases, which means as you go to shorter wavelengths, from IR to visible if you go, this efficiency is actually going to, as your band gap in your double heterostructure, as your band gap increases, the refractive index actually decreased, right. That is how the double heterostructure became. So, as your wavelength goes from IR to visible, so IR to visible, your lambda decreases, frequency increases, band gap increases, n decreases, and when n decreases, your efficiency because of Fresnel coefficient will start. As n decreases, what happens to this number 4n by n plus 1 the whole square? Would it increase or would it decrease? I would say 4n by n plus 1 the whole square, you write it as 4 divided by n plus 2 plus 1 by n. How would this behave now? As your n increases, would your denominator increase or decrease? It will depend on the magnitude of n or 1 by n. So, it is not very easy to answer, but you can plot it and check. Between 3.4 to 3.8, you can actually plot it and check. In that short range of frequencies, it depends on whether n is dominating or 1 by n is dominating, right. So, you can that is an exercise, you can plot and check what is the efficiency change as your n changes. Alright, but that is only one reason for loss of photons. And one more thing we have missed here is this formula for reflection coefficient will work only for normal incidence. This is a case when the light wave is incident normal. If the wave is incident at an angle, this formula will get modified, and it will get modified for the two polarizations. For the S polarization and the P polarization in your basic electromagnetics, you have different reflection formulas. But we are not going to do that detailed derivation or analysis, simply because the next effect that we are going to talk about will tell us that you are close to always normal incidence. Okay. So, the difference between the two polarization, the Fresnel reflect, the change because of the angle of incidence is not very much. And the next effect we are going to talk about is total internal reflection.